All right, let's connect some dots. We're going to take a recent Nobel Prize-winning breakthrough and link it to a theory that could, and I mean could, be the blueprint for our entire universe. Yeah, we're going from a lab experiment all the way to the very fabric of reality itself. Let's dive in. So let's just start with the biggest idea imaginable. What if space and time, the very stage our lives play out on, aren't fundamental? What if they're not the bedrock of reality at all? Imagine they're more like the image on a TV screen, woven from those bizarre, spooky connections of quantum entanglement. Now, I know that sounds wild, but stick with me, because we're going to see how scientists are actually trying to prove this right now. Okay, but before we can even talk about this incredible new picture of reality, we first have to understand why we even need it. You see, for all its amazing success, modern physics has a huge, gaping problem, a crack running right down the middle of it. And that crack, it's the massive conflict between our two greatest theories of the universe. It's really a tale of two realities. On one side, you've got Einstein's general relativity. It's beautiful, it describes the grand cosmic scale, planets, galaxies, where spacetime is this smooth, continuous fabric that gets bent by gravity. But then, on the other side, you have quantum mechanics. It's the king of the very, very small, atoms, particles, where everything is chunky, quantized, and based on probabilities. These two descriptions they do not play well together. They are fundamentally incompatible. And look, this isn't just some abstract problem for physicists in ivory towers. No way. This disconnect is the reason we're stuck on the biggest questions there are. Like, what is dark matter? Why is the universe's expansion speeding up? What in the world is going on inside a black hole or at the very first instant of the Big Bang? The honest answer is, we don't know. We can't know. Because we're missing the one thing that can bridge that gap. A true theory of quantum gravity. So, how do you solve the single biggest problem in physics? Well, what if the answer is to realize we've been asking the wrong question? There's a radical new idea that says space-time isn't the stage where the action happens. It's actually one of the actors. This is where we get to the Qmn-Modified Vacuum Theory, or QUV for short, and its central claim is, well, it's pretty mind-blowing. It says that space-time, the geometry of our universe, isn't fundamental at all. It emerges from the deep structure of quantum entanglement. You know that spooky action at a distance that Einstein famously hated? Turns out, it might not be a weird side effect. It might be the main event, the very thread that weaves the fabric of reality itself. Okay, you're looking at Einstein's masterpiece. For more than 100 years, this equation has been the law of gravity. The simplest way to think about it is like a cosmic rulebook. On one side of the equation, you have the geometry of space-time. On the other side, you have all the matter and energy, all the stuff in the universe. And the equation just says the stuff tells space-time how to curve, and that curvature tells the stuff how to move. Simple, right? Well, the QUV theory does something incredibly audacious. It looks at this century-old equation and says, I think you're missing something. It proposes adding a new term to the stuff side of the equation. This new term, Qμ, basically represents quantum entanglement. So the theory is claiming it's not just matter and energy that bends spacetime, the amount of quantum entanglement in a region can also be a source of gravity. Think about that for a second. It's basically saying that pure information has weight. And here's where it gets really, really interesting. This new term isn't just some abstract math. No, it breaks down into three separate real-world effects. You've got the alpha term, which connects space-time curvature to heat. Then there's the beta term, which says if you have a change in entanglement from one place to another, that actually creates a force. And finally, the gamma term says that the constant underlying fizz of quantum fluctuations in empty space, the vacuum energy, has a real gravitational pull. And the best part? These aren't just philosophical ideas. They are concrete predictions. Predictions you can actually go out and test. Okay, so we have these incredible, testable predictions. But how on earth do you test them? For decades, that was the problem. A great idea with no way to prove it. But now, thanks to a monumental breakthrough in physics, that has all changed. This is the moment our story moves from the chalkboard to the lab bench. It turns out some recent Nobel Prize-winning work has handed us the exact tools we need. We can now take these massive cosmic questions and actually investigate them on a tabletop. What these scientists did was figure out how to build and measure quantum effects in systems big enough for us to see and control. They basically opened a door to a whole new world of physics that we thought was locked forever. And this right here, this is the key that unlocks the whole thing. The secret sauce is something called a Josephson junction. This is the heart of that Nobel-winning work. Just think of it as a special kind of superconducting circuit. When you get it super cold, billions of electrons inside it start acting in perfect unison, like a single giant quantum particle. It's quantum mechanics, but scaled up to a size we can actually work with. And here's the kicker. QV theory predicts that the silent hum of the quantum vacuum should show up as a tiny but measurable voltage flicker inside these very circuits. So the experiment is actually pretty straightforward, conceptually at least. Step 1, you build one of these special superconducting circuits, a Josephson junction. Step 2, you use those incredibly sensitive, Nobel Prize-winning techniques to listen for any background electrical noise. And step 3, you look for a very specific signal. If the theory is right, you should detect a particular kind of hum, a noise signature that is the direct result of quantum vacuum fluctuations messing with spacetime. It's literally like building a microphone to hear the whisper of spacetime itself. And it doesn't stop there. The theory makes other predictions that are just as wild. I mean, get this. Could the physical shape of a circuit, its geometry, directly change the quantum rules happening inside of it? Okay, so QUV predicts that if you could zoom way, way, way in on spacetime, it wouldn't be smooth. It would be fractal, like a coastline with patterns that repeat at different scales. Now here's the cool part. The theory says this fractal structure is directly connected to the fundamental constants of the universe, like the fine structure constant that sets the strength of electricity and magnetism. So the prediction is that this constant shouldn't be, well, constant. It should vary ever so slightly across the universe by about 1 part in a billion. And guess what? Our telescopes are getting so precise, we can actually start looking for that tiny variation in the light from distant ancient quasars. We're hunting for the fractal fingerprint of spacetime. So let's take a step back. What happens if these experiments actually work? If we find this voltage noise or see these variations in the constants? Well, the implications are not just big, they're staggering. We're not talking about a new chapter in physics. We're talking about throwing out the old book and starting a completely new one. This right here just shows you what a massive paradigm shift this would be. Let's take dark matter, right? For decades, we've been hunting for some mysterious, invisible particle to explain why galaxies are spinning way too fast. We've built massive detectors, spent billions of dollars, and found nothing. QUV theory just walks in and says, hey, maybe you're looking for the wrong thing. It says there is no new particle. That extra gravity, it's just an entropic force. It's that beta term we talked about. It's the universe itself creating a force just because of how its quantum entanglement is arranged. The solution was there all along, woven into the fabric of reality. So the implications are just revolutionary. Let's just list them out. 1. Space-time isn't fundamental. It's emergent, built from quantum information. 2. This means the universe basically acts like a giant information processing system. And 3, and this is maybe the most exciting part for us right now, we can finally test quantum gravity. We don't have to just look at black holes or the Big Bang anymore. We can build experiments to probe the nature of reality in a lab, right here on Earth. And all of this leaves us with one final, truly mind-bending question to chew on. If space-time is just woven from quantum entanglement, and if matter is just a persistent pattern in that weave, then what are we? Are we and everything we see and know and love just complex, emergent properties of a vast, cosmic quantum computation? The idea is absolutely staggering, but the most incredible part? For the very first time in history, we might actually have the tools to find out.